All right, guys. Welcome to the third session. Third session, we're going to talk about monetary policy strategies and labor market dynamics. So 3 presenters. I try to be very strict so that we put them in half an hour time or maybe slightly less if they want to. Okay, first presentation is by Paolo Gelain from the FRB of Cleveland. And he's going to talk about optimal QE and QT. So, Paolo, do you hear me?
Yeah, I hear you very well, thanks.
All right, the floor is yours. You start. So you have 25 minutes for the presentation and 5 minutes for the question. And I give you not 5 minutes before the end and 1 minute before the end. Thank you.
Great.
All yours.
Thank you. Thanks. So let me first thank the organizers for including our paper in the program. I would have loved to be in Pretoria, but for some reasons I couldn't. So this is, as the chair said, the title of the paper is Optimal QE and QT, Quantitative Easing and Tightening. This is a joint work with Junior Mai from Norges Bank, Eric Sims from Notre Dame, and Cynthia Wu from the University of Illinois, Urbana-Champaign. Since Junior and I work for different institutions, the usual disclaimer applies. Let me stress right away that this is very much work in progress, preliminary work, and so we appreciate any feedback that you might have. Let me start with some motivation for our paper. So we all know that quantitative easing has become part of the set of policies used by central banks to intervene in crisis periods. Despite some studies have empirically investigated the effects of such policies on inflation and the real economy, there has been little assessment on how they should be why in this paper we want to analyze the set of optimal interest rate and quantitative easing policies that the Federal Reserve could have put in place. So I'm saying here could have put in place because we want to give a quantitative and an historical perspective to our analysis. And that's why the first step in our paper macroeconomic, financial, and central bank balance sheet data from 19 equilibrium model, which allows us to talk about quantitative easing policies. And let me stress that this first step of our analysis is very important, the step of the estimation, because only the estimation can tell which features of the model, which shocks in the model is important to explain the data. And this ultimately will determine which are the trade-offs faced by the central bank and how effective the optimal monetary policy can be or cannot be in stabilizing the economy. So once we have the estimated model, we can then proceed to run a counterfactual scenario analysis under optimal policy. This is a standard way to proceed in the literature. So we solve the model under optimal policy. Then we set all the estimated parameters at their estimated value. And then we feed the solution under optimal policy with the estimated shocks. In such a way, we recover the counterfactual US economy under optimal policy. Then we can compare such a counterfactual economy with the actual US economy and see how far they are apart. And we can judge how the optimal policy could have done over our sample in stabilizing the economy. So, of course, if we look only at our estimated sample, we look at the past, but we can also look at the future because we can project our counterfactual economy forward. And so we can evaluate an optimal exit strategy so that's why we have QT in the paper too. But for today, we don't have this exercise. So let me go through the related literature because this also helps me to highlight our contribution. So first of all, our analysis is very similar in spirit to the paper by Giustiniano Piumiceri and Tambalotti, AJ Macro, JPT, and a recent paper of mine with Furlaneto and Sanjani Taheri in the Review of Economic Dynamics, FGT. So they are similar in spirit because those papers also estimate a large-scale the SG model for the US economy, and they also run the counterfactual exercise under optimal policy, but they only focus on the conventional monetary policy. We, of course, add the unconventional part. Then there are a few papers in which they use a small-scale calibrated models with optimal QE, Harrison, Karadin-Akov, Sims, Wu, and Zhang. And so those small models are useful to set to get intuition of what's going on with QE under optimal policy, and to build intuition and to highlight some of the mechanism. But we all know that results that hold in small models might not necessarily hold in a larger estimated model. And one example that can clarify my statement is the divine coincidence result, the results that optimal policy can eventually stabilize inflation and output gap at the same time perfectly. So this result holds only in the smallest, simplest three-equation New Keynesian model that we can think about, but it doesn't necessarily hold in larger estimated model. Then there are a couple of papers in which there are large-scale estimated models with optimal QE. So those have different focus than our paper. So for instance, they look at the euro area. First of all, they don't run the counterfactual exercise, but most importantly, they have some limitation that we overcome with our analysis. Because for instance, they don't take into account the zero lower bound over the estimation. They don't they don't use balance sheet data in the estimation. And they don't look at the welfare optimal policy, which is, I didn't say yet, but which this is what we are after in this paper. Then there are a couple of papers that is worth mentioning that develop toolkit to analyze optimal monetary policy in general, Harrison and Waldron, and the Groot and co-authors. And in particular, this last one is they run optimal QE projections for the aftermath of the Great Recession using the Simpson-Wu model, which is 2021, which is the same model we are using here, but of course they use the calibrated version that they took from the original contribution. And lastly, I would like to highlight this paper recently published in the Review of Economic Statistics, which is very useful for our analysis, in which they estimate a large-scale model with QE. Actually, they use the Simpson-Wu 2021 model for the US, but they don't do any optimal policy analysis. So this is then our contribution. So in terms of the model that we use for our analysis, we use a New Keynesian DSG model featuring all the standard bells and whistles, like in Smets and Wouters, and all the necessary ingredients to evaluate QE policies, like in Simpson-Wu 2021. The basic idea of Simpson-Wu is that government and firms issue public and private long-term bonds, respectively, and those can be purchased by financial intermediaries and by the central bank. So the list of agents in the model is very long. I don't have time to go through all of them, of course, and those also because most of them are very standard. It's literally Smets and Wouters. So I will just focus on those agents that are less standard, let's say, to highlight some of the mechanisms we have in mind. And then we start with the goods producing firms in the form of wholesale firm. So this type of firm produces output using capital and labor according to a standard Cobb-Douglas production function. So this type of firm has outstanding coupon liabilities on long-term bonds, and we follow Woodford 2001 in modeling these bonds as perpetuities with decaying coupon payments. And this is the same structure that we use for long-term public bonds, okay? And then this type of firm is also subject to an investment in advance constraint, meaning that a fraction of investments must be financed by debt. So this type of firms has to issue long-term bonds in order to finance some of their investment. Now, this element, this feature, this ingredient is key, together with the fact that also banks play a non-meaningful role in the model, to explain why and how QE has effect on the real economy. Because if firms this type of firm has to issue long-term bonds to finance investments, and then those bonds are bought and held by the central bank, then you can imagine that there is a connection there. The other agent I want to focus a little bit is the financial intermediaries. These are sort of standard because they follow Getter and Karadi. So the main idea here is that intermediaries can abscond with some of its assets and default. And the fraction that they can abscond with private bonds is called theta, and it's a time varying parameter which follows an autoregressive process of order 1, and this is what we call credit shock, and this is also kind of standard in the literature by now to make this assumption. So given that there is this possibility to steal assets and default, there is also an associated enforcement constraint which states that the cost of doing that, of absconding with assets, has always to be greater than or equal to the cost of the benefit of doing so. So the benefit is actually the amount of assets that the intermediary can abscond with, and the cost actually is this VT variable, which is actually, so if you do that, if you abscond and default, you are not a banker or an intermediary anymore. So you lose the value of being a banker, which is a discounted sum of all future profits. And so this is the constraint that has to hold. And in other words, this constraint also says that creditors will only allow intermediaries to borrow up until the point where it is not optimal for them to default. Okay, this is also pretty standard. In terms of in terms of monetary policy, the conventional part, we assume that the central bank sets the interest rate according to a Taylor rule, in which the interest rate responds to inflation and output growth. And we also assume that the interest rate is subject to the zero lower bound constraint, which we deal, of course, with a macro switching approach. And then there is the conventional part, in which we assume that the central bank can hold either private investment bonds or long-term investment bonds or long-term government bonds, and it finances that with reserves. So you see there the balance sheet of the central bank. Then we can define the ratio between the private QE and the public QE over GDP, and we can define a law of motion for those two objects. And so we make the following assumptions. So if we are in normal times, when the interest rate is above 1, the gross interest rate is above 1, then QE policies are exogenous, and they simply follow an autoregressive process of order 1. On the contrary, if we are in ZLB times, when the interest rate is below 1, we assume that QE policy are endogenous, and so they respond in the same way that the interest rate does to the evolution of inflation and the output growth. Now, in terms of the data we use and the estimation strategy, so we use a bunch of US variables: GDP growth, consumption growth, investment growth, wage growth, hours worked, inflation, Fed funds rate, the Gilchrist and Zakrajek spread, then the central bank holding of private and government bonds as a share of GDP, long-term bonds, and the total amount of long-term government bonds. As I said, the sample goes from the first quarter of 1998 to the last quarter of 2019. I also put in brackets there 2023 Q4, because as I said in the beginning, we want to eventually talk about QT, so optimal exit strategy. And so we want to get timely evaluation there. So we need to estimate eventually the model with the most recent available data, which might be actually 2024 Q1 by now. And but dealing with the pandemic data is actually kind of tricky, so we might need to move to a stochastic volatility, and we are not there yet. And then, of course, in the end, needlessly to say, for the estimation of the model and also for all the other exercises we do in the paper, we use RISE toolbox. Here is just to give you an idea of how our observables look like over our sample, and just to highlight and that you might recognize the evolution of the Fed balance sheet in the first two charts as a share of GDP. Let me move to the results. So the first result I want to show you from the estimation is this smoothed probabilities, which is an indicator of which regime we are in. So in this particular case, the figure I'm showing here so if the smoothed probabilities is equal to 1, then it means that you are in normal times. If it's equal to 0, you are in the ZLB times. Then, as you can see, the estimation kind of identifies the ZLB period to be from 2009 Q1 to 2015 Q4, which is the period which I think all of us would agree that the interest rate was constrained to be 0 in the US. So now we are in a macro switching world, atoms in pair, and the same is true for valence decomposition. So we have two set sets of variance decomposition. So we have variance decomposition for normal times and variance decomposition for the ZLB, which go in the next slide. So here, this figure is messy. I understand that there are a lot of colors. There are many. The legend might not be that but please, if you don't want to do yourself looking at the colors, just to the figure. And so these are all the observables we use, and the variance decomposition is for 50 quarters. So let me start with the first two variables, the private QE and the public QE. So we are normal times. So as I said, QE policies are exogenous, and so they are following an autoregressive process of order one. So they are explained 100% by their own innovation, by definition. Then the rest of the variance decomposition is pretty standard. It follows really Smets and Wouters. So for instance, consumption growth is mainly driven by the intertemporal preference shock. Investment growth is mainly driven by the investment-specific shock. Output growth is a combination of intertemporal preference shock, investment-specific shock, and government spending shock, which is intuitive because Y is equal to C plus I plus G. Then real wage growth is driven by almost 100% by wage markup shocks. Inflation is very much driven by the price markup shock. Then we have the policy rate, which is driven in the short run by the conventional monetary policy shocks. And then over time, the investment-specific shocks become the most important driver. Finally, the corporate bond spread is actually driven by a good chunk by the credit shock, which is good. And then the rest is a mix of the other shock in the model. Let me start by this, since I'm talking about the credit shock now, let me highlight one important thing that stresses the importance of the estimation. So the paper by Sims, Wu, and Zhang, the famous four-equation new Keynesian model, highlight the fact that this credit shock actually appears, they show it analytically, appears in the Phillips curve. And they claim that this shock creates a wedge in the Phillips curve that breaks down the divine coincidence, even in the simplest four-equation model. Now, if you look at our results, the credit shock does not explain anything of any other variable other than the spread, and especially inflation. And this is a result of the estimation. So only the estimation can tell us how important this shock is. And the estimation is telling us that this shock is not important. So the problem highlighted by Sims, Wu, and Zhang of breaking the divine coincidence with that shock might not be so relevant in our case, because even if that shock appears in our Phillips curve, even in our bigger model, since it's not important to explain inflation, it might not generate any break of the divine coincidence. The other thing I want to highlight here with this variance decomposition for normal times is that the fact you see that private QE and public QE shocks are totally irrelevant to explain any variable in the model. Real or nominal doesn't matter. And this is kind of not surprisingly to me, because these are monetary policy shocks. And also conventional policy shocks are, as we all know, they are not very relevant to explain the rest of the model. And also this result of public QE and private QE actually is kind of in line and consistent with what Fabio showed before this morning. So does that mean that having QE policies in the model is totally irrelevant? Well, the answer is no, because as I said before, we have the ZLB times, which are actually 1/3 of our sample. And so what happens in ZLB time is the following. So first of all, QE policies become endogenous, as I said. So as you can see from the variance decomposition, that now they are not explained anymore 100% by their own innovation, but there are other shocks that appears to be important drivers of those two variables. And in particular, the private QE is now driven by a good chunk by the investment-specific shock. And this is also intuitive, because if you remember the investment in advanced constraint that I showed you before, you might easily understand why the investment-specific shock is popping up to explain the private QE. So the rest of the variance decomposition in ZLB times is very similar to normal times in a qualitative sense, but there is one important exception, which is inflation. So as you can see before, in normal times, inflation was almost around 80% driven by price markup shocks. Now, as you can see, half of the inflation variability is explained by the investment-specific shock. So this is intuitive to explain because I can refer still to the paper by Sims, Wu, and Zhang. They also show in that four-equation model that also the QE term appears in the Phillips curve. So now, why don't we see QE shocks explaining inflation, but we see investment-specific shocks explaining inflation now through the Phillips curve channel? Well, the reason is that both public and private QE shocks the standard deviation of those shocks is estimated to be so small that they are irrelevant to explain anything compared to the other shocks. On the contrary, when we are in ZLB times and there is this endogenous response through the QE endogenous response, you see that investment-specific shock, actually, which is an important shock to explain the economy in general, actually become important for QE itself and through the Phillips curve channel also for inflation, okay? And this is an important result because we know that price markup shocks are shocks that are relevant when it comes to talk about trade-offs, because those are shocks that generate large trade-off, which are difficult to be faced by the central bank. So since in ZLB times we have this endogenous results that we reduce the importance of price markup shocks to explain inflation, we give the possibility to investment-specific shock to explain inflation, will imply that optimal policy could be actually more efficient to stabilize inflation during these times. Okay, this is all for the variance decomposition. So in the last 5 minutes I have at my disposal, I'm going to talk about optimal policy. So we have different options here.
4 minutes.
Yeah, 4 minutes, perfect. So different options. So we can maximize the true welfare function. We can maximize the second order approximation of the utility functions, adopting then a linear quadratic approach, which is the most standard in the literature and the one we would like to have as a baseline case. We can minimize an ad hoc loss function. We can optimize simple rules in order to maximize the true welfare function, maximize the second order approximation of the utility function, minimize an ad hoc loss function. For all these cases, we can impose or not the zero lower bound, and we can go with the case of commitment or discretion. So for today, as I said, this preliminary work, we can only show you the results out of optimized simple rules in order to minimize an ad hoc loss function with only inflation or the variance of inflation as an objective. We enforce the zero lower bound under optimal policy, and we go with the case of commitment. And the functional form we use for optimal simple rules is exactly the same functional form that we use for the estimation. So the rules I showed you before, but instead of estimating the parameters, we optimize them in order to minimize the ad hoc loss function. So before showing you the counterfactual exercise I was promising since the beginning, let me just quickly tell you what we know in terms of from the empirical literature in terms of policy trade-off and implication for optimal policy. And when I say empirical literature, I refer to Giustiniano Primiceri Tambalotti paper and my paper with Rudaneto and Taheri. So what do we know about policy trade-offs? So both those papers show that monetary policy trade-offs are empirically small. And the implication for optimal policy of that finding is that both papers show that optimal, and let me stress, conventional only monetary policy can achieve a trinity, meaning that it can achieve a very good stabilization of output gap, price inflation, and wage inflation at the same time, which is a sort of an extension of the divine coincidence concept into a large-scale DSG model. But all that might not be the case in our model because we have different features, different shocks, but most importantly, QE policy. Okay, with this in mind, let me show you the counterfactual exercise only in terms of output growth and inflation. So the reddish lines are the counterfactual economy under optimal policy, and the blue lines are the actual US economy over our sample. So as you can see, optimal policy can actually stabilize to some extent inflation and also output growth. Output growth sometimes is very destabilized, like during the Great Recession or towards the end of the sample. So the stabilization properties of optimal policy here is way far from what we can see in JPT. But to be fair, the comparison is a bit unfair because we are doing optimized simple rules. JPT and FGT, they actually do optimal LQ welfare analysis. So if we do the same, then we might get similar or different results from what you see here. So in terms of implementation of optimal policy to achieve the output growth and inflation outcome that I just showed you in terms of instruments, you see that the interest rate should have kept lower for most of the sample. For QE, it depends on if you look at the public QE and private QE, the prescriptions are different. So public QE looked like a bit close to optimality over the ZLB period and far from being optimal in normal times. The opposite seems to be true for private QE, where it seems to be very close to optimal in normal times and way different or far from optimality during the ZLB times. All right, let me conclude. So in this paper, we studied the mix of optimal conventional and quantitative easing policies that the Fed could have put in place. So we first quantified the relevant trade-offs by estimating a new Keynesian DSG model with banks and QE policy. And we find that trade-offs are not very small, as previously found. An implication for optimal policy in the form of optimized simple rules is that it can achieve some stabilization of inflation and the real economy, but not a strong one. So we have somewhat a large deviation from the divine coincident result. But the most important sentence in this slide and for the whole presentation is that results are preliminary and could change by the inclusion of most recent data in the estimation, and most importantly, by considering other characterization of optimal policy, most notably the welfare maximization, instead of relying on optimized simple rules. Thanks a lot for your attention. I'm looking forward for
many thanks, Paolo, for interesting presentation. This is time for the questions, guys. Any question from the room? No? Okay. We got on the line. Yeah, you go ahead.
Is there any intuition? I noticed in the zero low bound times, it seems like the policy should be to private QE and the other one public QE in the other times. If I read that correctly, is there a strong intuition for that?
Right, not at the moment. As I said, it's preliminary, and most likely this exercise would not even appear in the final version of the model, because optimized simple rules is a nice way people have done, but we are mostly interested in a welfare-based type of analysis. So we didn't have the time to invest intuition behind the results. We are just showing what happens, and maybe the idea here decently the stuff going on. So I'm sorry I don't have a strong intuition for explaining the evolution of the variables under optimal policy.
Okay, we have some online question, I guess.
Hi, thank you. Yes, online question. Long-term bond returns differ from the expected short-term ones. Linear first-order approximation, even RS, suggests that it is equal. What have you done with different average returns? Then there's a second question, which let me pose now, and then you can answer both. Do you compute optimal policy conditional on posterior mode? Do you try such policy at mode with draws of parameters? How good is the optimal policy that does not care about parameters uncertainty? Thank you.
Yeah, so let me start from the last one. So now, yeah, we took the posterior modes and we didn't try to draw from posteriors to get sense of the uncertainty around our optimal policy results. We can do that. That's a very good suggestion. The first one, I'm not sure I got it entirely. The difference between short-term rates and long-term rates.
Okay, let me repeat. Sorry, I think English is not the first language. Long-term bond returns differ from the expected short-term. Linear, so linear first-order approximation, even RS, suggests that it is equal. What have you done with different average returns?
We didn't check if they are equal or if they are different in our model. We rely on an existing model, which is Simpson-Vu, and there is no proper term structure, I guess. We have long-term returns model as Wood for 2001, as I said. So I guess there is a one-to-one mapping between short-term and long-term bonds in that respect. So yeah, I'm not sure I answered the question, but this is what we have.
Thank you.
Okay, many thanks, Paolo. Many thanks. And we go to the next presenter now.
Thank you.